All right, 12.2b, transforming with logarithms. So using a power model to describe a relationship is the same thing as taking the log of both x and y. So I want you guys to write down power model, and we're going to log both x and y. This right here represents a power model, and they use this exponent p to help you remember a power model. So maybe we're cubing something or squaring something. And then A and P are both constants. So you might want to make note of that. And so what we can do is take the log of both sides in this power model. So I'm going to log this side here, and I'm going to log this side here. And I don't know if you guys remember this, but we can expand this log. So right here we're multiplying. Anytime you multiply with logs, that changes to plus when you expand. So I get log A plus log x to the p. And then any power that you have can go in front of the log. So I get log y equals log A plus p log x. And what we end up with is a linear function. And p represents the slope, since we logged both sides. And we got a variable here. This log A, because A is a constant, this turns into a constant, which is our y-intercept. All right, and then I have a log in front of x, and I have a log in front of y, my input and my output. And so if a power model describes the relationship between two variables, a scatter plot of the logs of both variables should produce a linear pattern. So we're going to look for a linear pattern after we log both sides, and then you know a power model is a good fit. So for example, let's return to the fishing tournament from the previous example. Our goal remains the same, to find a model for predicting the weight of an Atlantic Ocean rockfish from its length. We still predict the power model of the form weight equals A times the length cubed based on geometry. Here, once again, is a scatter plot of the data from the local marine research lab. So we have just our length here and our weight here, and we're increasing. And earlier we used cubing the length or taking the cube root of the weight, but this time we're going to try logging both sides and see what happens. All right, so we took the logarithm with base 10 of both values for both variables, the input and the output. And here's our output. So notice, I know this is small, but you always want to read these graphs. This says log of the length, so that's log of the input, and log of the weight. So if you're using a power model, you are logging both the x and the y, or the input and the output. That's important. And then hopefully you notice a linear pattern. Okay, then we're looking at the residual plot, which shows no leftover pattern. So again, we have a linear pattern as a good fit. They give you the output, all right? Now you have to write the equation for this. But let's do part A first. Based on the output, explain why it would be reasonable to use a power model to describe the relationship between weight and length for Atlantic Ocean rockfish. So if it says power model, that's when you log both sides. And the reason that it works is because we have a linear pattern, or a linear scatter plot. And of course, no leftover pattern in the residual plot. Okay. And now we want to find the equation of the least squares regression line, and be sure to define any variables you use. This constant, this is still our A, or our y-intercept, and this is still our b, or our slope. And notice it's log of that length, okay? So we're logging both the input and the output. Our output is log weight. So I'm going to start with log of the weight. And again, this is predicted, so I'm going to put a big hat over that whole thing, equals, Our constant goes first, my y-intercept, negative 1.8994. Okay, so that's this number here. And then I have the slope, but we put that in front, and then we have our log. So plus 3.04942. And then I do log of the length. Okay, slope goes in front of your input number, and our input is log of length, just like it says here. So there's our equation. Yep, so there's part A and B. All right, go fish, making predictions. So suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish that's 36 centimeters long. Use the model from part B in the previous example to predict the fish's weight. So we're using the model we just had, or we just wrote down. Log weight equals negative 1.8994 plus 3.049 or 4942 log, and I want to know it's 36 centimeters long, so I'm going to plug in 36 for the length. Okay. Now hopefully you guys remember some of these skills from your previous class, but we're going to actually plug this whole thing into the calculator and evaluate that first. So you guys might want to get a calculator and try this and make sure you remember how to do it. So negative 1.8994 plus 3.04942. And we got to find the log button. So control and the log button's right here above the 10 to the x. Okay, anytime you don't see a base, it's a base of 10, and then plug in 36. Oh, I had an answer in here. We need a negative sign right here. All right, so 3 point, oh, I think I messed that up. Yep. Can't use that one. There we go. Negative 1.8994. Okay, there we go, 2.8464. Okay, so I still have the log on the other side. So log of, and I'm just going to put W, equals 2.8464. So in case you forgot how to get rid of logs, so there's really a base of 10 that you don't see, and I'm going to put it in exponential form by looping it, and that gets rid of the log here. So it's 10 to this power 2.8464 equals the predicted weight. Okay, now I can plug that into my calculator. And I get 702.134. Okay, and this is in grams. We're talking about the weight, the predicted weight of the fish when it has a length of 36 centimeters. All right, so now we're going to do exponential growth. So we just did a power model. Now I'm going to do an exponential model. So you might want to write that down. Suppose that you invest $100 in a savings account that pays 6% interest compounded annually. So after a year, you have $100 times the 6%, which is the $6 interest. And you're going to add that, of course, so you have $106 total. So this is just representing an exponential model. You guys have seen this before. If you do it twice, okay, you can do squared here. You can just multiply by that in the front. Hopefully you guys remember what exponential kind of looks like. So here's our original graph, which definitely looks like exponential growth. So as time increases, your balance starts drastically increasing at that 6% interest. Here we've just got an input-output table. And so basic exponential models, you guys need to write this down, look like this. Y equals AB to the X. A is always your initial amount that you started with, so $100 in the last problem. And B is your growth rate. Okay, so that was 6%. So for this one, if we have an exponential model, it describes the relationship between x and y. We can use logs to transform the data to produce a linear relationship. The only thing is, we only take the log of the output. So in the power model, we took the log of the input and the output. So watch what happens when we log both sides. So I'm going to take a log of this side and a log of a b to the x. Okay, I'm going to expand this just like I did before. So I'm multiplying, which means we add. So I get log a plus log b to the x power. The x goes in front. If you guys don't remember this, it's not overly important. Okay, so don't worry. And it looks like this. Remember that a and b are constants, right? Which means this whole thing is a constant. You could plug it into your calculator and just get a constant. Which means we have a y-intercept here and a slope here, and we really only end up with log of y. All right? So we only log the output variable, or the y. So you might want to write that down with an exponential model. You got to know the difference. Only log the output. Okay? With a power model, log the input and the output. So let's look at, we've got some Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors in an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are the data on the dates and the number of transistors for Intel microprocessors. All right, so here we've got the original data, which looks like exponential growth, so years since 1970 and the number of transistors. And then what we do here, and again, you always want to look at the graph and what they did. They took the ln, same thing as the log, okay, of just the output, but they did not take, there's no log or ln in front of years since 1970. Did we get a pretty straight line? Yes. So if you get a straight line and you only did the log or the ln of the output, what model are you looking for? Exponential. All right, so a scatter plot of natural logs of the number of transistors on a computer chip versus years since 1970 was shown. Based on this graph, explain why it's reasonable to use an exponential model. So based on the graph, you guys, it's reasonable because it's roughly linear. So you can write it like this. The scatter plot of x, comma, ln y. So my input stayed the same, but I took the log of the output, or the natural log of the output, is roughly linear. And so an exponential model is a good fit. Okay. So here we have mini tab. Give the least squares regression line. Be sure to define any variables that you use. All right, so this time my output has an ln in front of it. So I've got ln, and what the output is the transistors. And again, you can look at your graph, ln of transistors. Okay, and again, it's the predicted output is equal to, okay, here's my y-intercept, 7.0647, and then my slope goes next, 0.36583, okay, and then there's no ln here because this is the exponential model, and so what goes here is just years since 1970. Okay, if you use x and y here and here, just make sure you define it. All right, use your model from part B to predict the number of transistors on a computer chip in 2020. So 2020 is how many years since 1970? That'd be 50 years. All we're going to do is plug 50 in right here. So ln of t, 7.0647 plus, and I'm going to plug in 50. Okay, plug this whole thing into your calculator, and you get 25.3562. Over here, how do we get rid of the natural log? Hopefully you remember the inverse of the natural log is e. Gotta know that. That cancels that. So now I have the predicted number of transistors is e to this power. That is an exponent, so be sure when you plug it in, you do this E button, whoops, and then plug the number into the exponent. And you should get a really big number, 1.028 times 10 to the 11th transistors. That's like 100 billion. All right, power or exponential model. So use logarithms to transform your data. You got to use guess and check sometimes. All right. So you want to plot first your x and then plot where you log the outputs only. Okay, and if you log just the outputs and you get a pretty much linear graph, then you have an exponential model, and you want to use this equation where you only log the y. All right. If you log both the input and the output and you get a mostly linear graph, then you're looking for a power model, and you're going to log both the output and the input, and it looks like this. All right, so make sure you write down your general formula for each of these and then which is which. So we've got a team of astronomers announced they had discovered that if there appeared to be a new planet in the solar system. They had first observed this object almost 2 years earlier using a telescope. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of 9.5 billion miles from the sun. All right, so could this be a new planet? Here's the data on the distance from the sun and the period of revolutions of those planets. Note that distance is measured in astronomical units, or AU, the number of Earth distances the object is from the sun. All right, so we've got our distance from the sun and our period of revolution. Distance, period. All right, so here's our original graph, which has a little bit of a curve to it. And we're going to look at both graphs, okay? It's hard to read this, but this is ln and just distance, all right? Over here we have ln of the distance and ln of the period. So which one's more linear? Obviously this one is more linear, this one is curved. So if you have where you took the log of both, that would be a power model that is a better fit. Okay. This one we only did the ln of the output, this stayed the same, and so this is an exponential model. So why is a power model more appropriate? Because we have a more linear graph when we take the ln of both the input and the output. Okay, and then you would give your equation, which we just did, and then you would use your predictions and plug in 102.15 to get an output, just like we did before. So I do want to look at this. This is new, so pay attention to this. Last thing. So we have a residual plot for the linear regression in part B, is shown right here. Do you expect your prediction in part C to be too high, too low, or about right? So in part C, we plugged in 102.15 AUs, which was the distance the planet is away. So I'm going to take the ln of 102.15, and we get 4.626. All right, so this was just when I plug in that distance away to the log. So remember that a residual, this is from a previous chapter, and I'm not exactly sure, is equal to actual minus predicted. So each of these distances represents actual minus predicted. This right here is our predicted distance. All right, so ln of the distance, 4.6, so that's about right here. We could add a little dot, right? So it looks like it's going to be above that residual line. So my predicted would be plugged in here. My actual is going to be higher because I got a positive number